Well, hello and welcome to SkyTour Livestream tonight. It is April 28th, almost the end of April, and I am here as always with Darrell Mason. Hello, Darrell. How are you?
Hello, Marc. I'm good. You?
I'm just fine, thank you. So, and Tim F is the first one here. Hiya, Tim.
Hello, Tim.
Good to see you. So
Hey,
we're
where's everybody?
Oh, they'll be here. I only just put the stream up, so.
Yeah, I took a bath this month already. There's Bonnie.
Oh, Anahata 77. Hi, Bonnie. How are you? So good to see you, Bonnie. Am I going to see you in Denver? I don't know if you're going to go, but Darrell's threatening to come too. And he says if he does come, and he says he's going to buy us dinner. That's what he said. I heard it from his own mouth.
If I don't have to pay admission.
If he doesn't have to pay admission, that's right. Well, yeah, I got to figure out how to do that. I'll work on it.
All right.
It's sort of an a la carte thing, so people don't they don't pay for like one price. The cost is like $150 for the whole thing. So we'll see what we can do about that. I know it. Okay, so we're just looking at Sirius right now, just to kind of, while away the moments while it's still light out there. As you can see, that's how bright it is out there right now. That this thing up here is misleading. That's the sky. It's misleading because it's really stopped down to show us the interior of the observatory. Hey, JSCO, how are you? And Satisfying Animations, long time no see. Good to see you back. How are you? I hope everything is going okay for you. And I'm looking forward to tonight. We're actually gonna, we'll do a relatively. It's probably gonna be an hour and a half to 2 hours, not that long. I got a lot of filming to do tomorrow for a TV thingy, and so I got tons of questions I have to go over, and it's not a script per se, but just the nice thing is I'm going on this show as an astronomer, not as a UFO guy. It's the first one ever, which I think is kind of cool. It's about time. Yeah. And luckily they're not going to ask me too much historical astronomy, but they do want to talk about Epicurus and Aristotle and the Aristotelian universe a little bit. And they're going to talk about Bruno and Galileo, how they're both tried for heresy a little bit, and I just, and Copernicus, of course, the geocentric model that Copernicus kind of pushed. They're not going to talk about Ptolemy's epicycles, which I think is kind of should be talked about, and I might bring it up myself, but I have some props. I have things I'm going to bring to kind of show off some of the concepts we're talking about. Yeah, the series is looking good. It's looking good.
I was reading recently about Copernicus. There's a book out. It may be recent. I'm not sure it's new.
Okay.
Called The Book Nobody Read. It's about Copernicus's book. It's supposed to be an interesting book. It sounds kind of unusual.
Yeah. Well, I mean, what was it, Plato who wrote Almagest? Or Almagest?
I don't remember.
Yeah. And it was his version of the heavens, which included the epicycles, which are, if you have a planet going around in an orbit, you have a issue when you have another planet going around in an orbit and you're observing this planet that's going in its orbit from yours. You see the planet make a weird spiral in the sky. It goes back on itself and then comes forward again. That's called retrograde motion. And to explain that, as Darrell knows, Ptolemy came up with an idea that these planets are going in these large circular orbits that explains this, because they thought the Earth was sitting still and everything was moving around the Earth.
Yeah.
Common mistake. A very common mistake.
The epicycles were part of what they call the clockwork universe nowadays, I guess. Trying to explain the motions, and they even had epicycles built into what are they called? Orreries?
Orreries, yeah.
Yeah, that simulated that backwards retrograde motion of the planets.
And what's interesting is it didn't work for all cases, but they didn't know how to fix it. Because, when you look at Mercury's retrograde motion, you see more of it than you do, say, with Jupiter. And they didn't know how to explain that. And their mechanical systems couldn't show it. And that was kind of an issue for them.
Well, that's the whole thing with Mercury and Venus being closer to the sun than we are.
Yep.
Why we see retrograde motion from them.
Yep. And more of it than, say, with Mars, Jupiter, Saturn, and so forth.
Oh, yeah.
It all has to do with the period around the sun that the planets take to go around. And I think it's really just a fascinating topic. And to be honest, that was the part of astronomy that I wasn't all that interested in. I really wanted to dig into the meat of what makes a planetary nebula. What's the chemistry? What's going on in there? What's the science we know? And how do we know it? That's really what I wanted to learn. And so that's kind of where I focused my attention. And then once I realized how exciting that all was, and I started to see that the stuff about exoplanets was coming out, I was like, whoa, there's my world. And I just love to just jump right into exoplanets. Just amazing stuff. Welcome,
yeah.
Marc.
Well, history is one of my, not a hobby, but an interest, and history of science is part of that, and thus history of astronomy.
Yeah, it is.
I think you've seen that diagram, that illustration before. It may have been from one of Flammarion's books that it's the guy sticking his head out through the starry sphere.
Yeah, actually, that was on the front of my Cosmology book.
Huh.
That was the cover, the hard cover. It was a hardcover book, and it was actually the cover of my Cosmology book.
Yeah.
Yep, really fascinating. All right, let's go and try and focus a little now. It's dark enough. Let's see how many stars we get in our focus. Well, all right, we'll try it. It might not be quite enough, but we'll give it a shot anyway. Okay.
Well,
so yeah,
summer's coming.
Yeah, it is.
Yeah, I noticed. Just a couple of days ago, the sun was setting here at 7:45, and now it's setting at 7:49, and it's gaining 2 or 3 minutes every day.
Yeah.
Setting later.
Pretty soon we're going to have to start streaming at like 11 p.m. We've done that before. But
well, that's one reason I don't like daylight savings time. The sun sets late enough in summer anyway, and then just making it set another hour later, it just
it's
puts
maddening.
things off.
Yeah.
Inconveniently.
Yeah. Yeah, I'm not happy with that, but you know what? We'll deal with it.
Yeah. The other side of the coin was, if it wasn't for daylight savings time, during the summer, the sun would be coming up at 4:30 in the morning, or even earlier, depending on where you are.
Yeah. I'm wondering where they are. I didn't check that legislation to see if daylight savings time is going to be a permanent thing again. They tried it back during the gas crisis, if you remember, and it was a dismal failure back then.
Yeah.
All right, let's
I don't know
who's position here.
The Senate, I guess, has voted in favor of daylight savings time year round.
Yeah.
I don't know who keeps filling their heads with this stuff. They don't know squat, Their handlers are telling them what to vote for.
Yeah, because they have no clue.
People want.
Yeah, they have no clue.
Yeah.
That is so true. No clue, so true. Too bad, so sad. Yeah, so these guys, They have no idea what they're looking at, but you know what? I can't tell you. Hold on, I gotta bring my gain up here. I think we can go up to about 200 now. There we go. There we go.
You never did go above 250 last night.
I know, and that was specifically because I didn't want to lose detail in the galaxies. Because when you go really high on the gain, you get more noise, which obviously you know, but it was just for the people listening.
Yeah.
So we're gonna stay at 250 tonight anyway. And I set the guide here already to be as optimal as I could, so we want to test that maybe with some longer exposures. So, alright, let's see. Oh, are you talking about... Is she talking about this? Is she talking about this right here?
I assume that's what she means.
Yeah.
Is that what you mean, Bonnie? That circle around the bright star?
This is the brightest star in the northern, well, in the sky. So this is an artifact of the imaging system that we're seeing. It's called a halo. And so if you see me looking left, by the way, this is the chat screen and the broadcast system, and then over here is the actual live observatory feed. So when I look here, I'm looking at what you're seeing. When I look over here, I'm looking at the live observatory feed. I'm sorry, the broadcast feed. So that's what you see when I look in these two directions. So, all right. Well, it's getting kind of dark. Where should we go now? I have some ideas.
For what you started to say a minute ago, what's the brightest star in the northern sky?
Sirius.
Sirius is, well, it's below the equator, isn't it? Hi, Izabela.
Oh, good. Isabella's here. Yeah, no, I wasn't. I was talking about the brightest star in the sky. I didn't. I don't know which star would be considered the brightest star in the northern sky. Is it? I was gonna say Aldebaran or Arcturus, but.
Yeah, Arcturus.
Yeah, because. All right.
It is very marginally brighter than Vega. Arcturus is the fourth brightest star in the sky, and Vega is the fifth, just by a whisker.
Okay.
Izabela's here.
I see. Welcome, Izabela. Okay, so let's, now that we've got focus and a potentially dark enough sky to go check some things out, let's do that. First things first, let's bring up the things that we know we can see. Alright.
Oh, look at Orion there. Rigel's about to touch the horizon already.
And it's hardly, yeah, and it's only, it's only 8:02 out in the observatory.
Yeah.
No. You know what? Should we try one last view of Orion Nebula if we can get it?
Oh, if you want, sure.
Yeah, why not, right? Let's go.
It'll be pretty low.
Yeah. Yeah, it's pretty low. Let me see the altitude. Actually, it might be too low already. Oh, it is. Yeah, we're too low. We can't see Orion. Sorry.
Oh, yeah. Well.
Yeah.
That's kind of a sad milepost for the year every year. Then it'll come back up in the morning sky. It'll be up in August.
That's right.
July, August before sunrise.
And meanwhile, we're not going to want to see Scorpios and Sagittarius go.
Yeah. And actually, if you watch Stellarium this time of year, Orion sets and Scorpios rises.
That's right.
And that goes back to Greek mythology, where the scorpion killed Orion, stung him on the foot. And the gods put him in the skies and separated them as far apart as they could, so they'd
Never
never
have to
fight
see it.
again. And
Yeah.
so Orion sets, Scorpio rises, Scorpius, and Scorpius sets, Orion rises.
Yeah.
I have to guess, well, it's mythology and it's fanciful and all, but there is a grain of truth in it, just in saying that when Betelgeuse sets, Antares rises, and vice versa, things like that.
Yeah, we still got some sky glow in the west, according to our stellarium evening twilight measurement here. But we can still get a look at some cool things. Let's actually try. I did this last time, but we'll try it again. We're gonna see if we can zip over to the Seagull Nebula and get an idea of how well it looks. I'm out of focus again. Oh, now I'm gone entirely. What's going on here? Might be the light. Nobody's supposed to see me, I guess. I will fix that by doing this. Yeah. It's the intensity of the light that causes that. Interesting. Alright, so here we are. We're on Sirius as our waypoint star, and then we're going to move to the Seagull Nebula. And I have the gain at 250 and only 1 second exposure, but you can see something here. Let's maximize our hypered view. Yeah, you can see the blue of the sky is still here, so this isn't going to be very helpful to us. But it's kind of a little waypoint. Helps us see what's going on. Let's do a 12-second shot, even though it's just a little bright. Michael Klagas, how you doing? Oh, Pillars of Creation will be in the summer. Yep. As you know. Izabela says, oh my god, a couple of years ago my brother was mocking me for my UFO interest. Now he is sending me old fake UFO videos on Skype, and I have to fix his mind. That's funny. Alright, let's go in here and do a live stack of the Seagull Nebula and see. I don't expect it to look very good, guys, because it's still light out a little bit, and so it's going to be a misleading image. It's going to look crappy. Let's do this. Fix the dynamic range issue, and color correct it. There's the head of the seagull right there. We can see it, but it's sort of a bright sky still, so that's why we can't really see it too well yet. Although I could adjust the dark level a little. Let's just bring that dark curve over. Yeah, so you can see that. These diagonal lines are an artifact that I'm going to fix when I go out there. I talked to the people out there today, and they're going to redouble their efforts to get the Starlink connection up and running. Everything is out there, ready to go. It just has to be installed.
Which
Ethernet
Starlink?
Adapter.
Yeah.
Starlink 40 megabit.
Yeah. What I was wondering was, is it on the computer in your observatory or on their computer in their home?
Well, the router comes into their house on the property.
Okay, and then you just have to plug a dongle in somewhere?
No, I have to actually plug directly into the Ethernet port. Oh. And I thought that the Ethernet port existed on the Starlink router because it always did. But they started making them without Ethernet, and everything was just Wi-Fi. And I had to spend $15 extra of pittance to get an Ethernet adapter, which plugs into the router on a proprietary cable, and then has one single Ethernet port that you could then take out to go to a switch and put all kinds of things in. Let's bring our nebula back here. There we go. It's getting darker out there. Color correct. And then bring our dark level over a little bit. There we go. Alright, this will get too bright and we'll bring it down. I just want to get my color corrected here. Alright. Look at that dark level going. This is the Seagull Nebula.
Did something just shut off on your end?
No, why?
Oh, I hear it again now. Okay. I hear kind of a whirring sound. It went away for a moment, and now it's back.
Is it this?
Yeah, sounded like.
Okay, that's the heater. That I can't do without. Just technical equipment. Yeah, I gotta keep that running.
Running a heater, and it's almost May.
I know it. Let's just bring this over. Let's check out our guiding and see if we've got anything to fix here. A little bit, yep. All right. All right. So now I'm going to clear this, and we're going to start again. And we're just waiting for it to get fully dark. That's, you know, so might as well do it on an object, right?
Sure.
Sure. So how are you guys all doing out there? I see Judy just came in. Hi, Judy. Nice to see you. Tim F. was first here to say hi to us, and then Bonnie came in, followed by JSCO 77, Satisfying Animations, and I think after that, Izabela came in and joined us. And then we had... who do we have? We had Scheiben is here. Hey, Scheiben, how you doing? Yeah, it's nice to see you. And of course, Judy McClelland. So anyway, I think that we're just getting through the moments here where we have a darker sky. We're just letting the sun set further. Yeah. It's a beautiful nebula, the Seagull Nebula. Awful lot of dust and gas in this location. It's just gorgeous. I'm going to bring up the dark level just a bit so we can see some more stuff in there. That's cool. And we've stacked 8 of these, so I'm going to just push this a little now. And see a little more detail. Wow, that's pretty. Oh, I can't wait for the elephant's trunk again, and some of the beautiful nebulae in Auriga. You could probably still see those, but they're going to be kind of low right now.
Yeah, you're talking more like, what elephant's trunk? I'm trying to remember. Cepheus?
Yeah.
Yeah. That'll be late summer toward fall.
Yeah. It's directly below the North Pole right now, roughly. Okay. Let's drag this over a little.
Shaven, are you asking how many light years we have to go to reach the object on screen?
Yeah, that's a good question. And this object is it 5,000 light years away? Let's find out. Oh no, it's only 1,800. So it would take 1,800 years to get there at light speed. And that's how long the light you see has taken to get here. Just about 1,800 years. The thing is, at the fastest possible speed we can go, to go 4 light years would take us about 12,000 years. So divide 1,800 by 4 and multiply it by 12,000 years, and that tells you how long, with what we know now, what we have now for propulsion, how long it would take us to get there. And as you'll find, it's just a ginormous distance. Something we just cannot do at this point. We definitely need to warp space. I like warping space. I really find it enjoyable. That's gorgeous. Look at, see, with each stack, it's coming in more crisp and clear. More of the noise is going away.
Yeah.
We know what this is for now, so I'm just gonna pull that off the screen. We don't need that.
So where is the Seagull?
The Seagull is literally just north of Sirius.
I mean, in the image.
Oh.
Trying
Okay.
to visualize the Seagull.
Right. Well. Oops. There's Sirius. So that's my. Okay. Right there. Anyway. Okay. So the Seagull. I think this is the head of the Seagull here, and these are the outstretched wings.
Oh.
That's what I'm guessing. And I think it might have its head turned, this way. So you see its beak here, or the crack in its beak, the mouth. I'm not sure. Seagulls look different around the world, so. I don't know what kind of seagull looks like this, though, to be honest with you. I don't know. It's the most ridiculous thing I've ever heard.
I was amazed when I first moved to Colorado so long ago.
Yeah.
Up in the mountains to see seagulls up there.
Oh, yeah.
They were flying around the lake up there.
Yeah, they will spend time around fresh water as well.
Yeah.
Michael Klages says, what if space is already warped? Well, it actually is in some ways, because you have to remember that when you're looking at space, you don't see the warpage caused by gravity to the space-time fabric, and that space-time fabric is subject to the mass that sits within it. The mass has gravity, and gravity warps that space-time fabric. And so this understanding space-time fabric will help you understand black holes, right? Because when you look at a black hole, you're looking at an object that they always say its gravity is so intense that not even light can escape it. And while true, that implies that light is getting pulled in by gravity, okay? And it's not. Light has no mass. Light is not subject to gravity. Oh no, what does that mean? Well, what it means is light follows the curvature of space, all right? So if you have a very deeply curved space, light follows that curve. So beyond what's called the event horizon of a black hole, the space becomes so deeply curved that the path out no longer exists for light. The light follows the curve in, and then is going to circle inside the black hole for eternity. And that's basically what's meant by not even light can escape. It's really a two-pronged question. It's, yes, light can't escape, but light has no mass. It has momentum. It has a relativistic mass. And, you're familiar with the famous equation, E equals mc squared. Well, actually, if you want to know the full equation, it's E squared equals momentum squared times the speed of light squared plus mass squared times the speed of light to the fourth. Okay, that's the actual full equation. And why am I telling you this? Well, because light doesn't have rest mass, which is mass that's not moving. Okay, and so E equals mc squared applies to anything but light. It really doesn't apply to light. For light, there is no mass, so the mc squared goes away. However, light has relativistic momentum, and that is denoted by the Planck constant h times the frequency of the light. So that's the relativistic momentum, right? Because energy translates to momentum for particles of light. Isn't this crazy? You're getting a physics lesson. You didn't even want it. But the thing is, so what that means is when you're talking about light, now we're talking about, for instance, just the difference between the p squared c squared plus plus m squared c to the fourth. The mc goes away, and you're just left the p squared c squared. You just left that term, and that is the energy of light, right? But if you're talking about something with mass, then there is no relativistic momentum, and that is zero. All right, and you're just left with the mc squared. So it works for the both ends of the boundary conditions, which is what we call that. So I'd have to write it down and show you, but I don't dare, because this is an astronomy fun stream, not a physics class. But if you have questions about it, go right ahead. Judy says this looks like a parrot. I can see that. I agree with it. This is the eye, and here's the beak, and it's looking at you just before it grabs you and bites you. Scheiben says, can't we see black holes via telescope? In a sense, yes, we can, but it depends what type of telescope we're using. In a visual telescope, no. We can see sometimes the jets that might emanate in the visible spectrum out of the north and south poles of a black hole, but we can't see the actual black hole itself. For that, we need a different type of telescope, and that type of telescope is a radio telescope. And we can also use an infrared telescope to see the heating that goes on by a black hole. Now, the Event Horizon Telescope sounds like one telescope, but it was actually 8 or so different radio telescopes, all aiming at the Virgo galaxy, Messier 87. And what they saw was a perfect rendering of exactly what they had theoretically predicted a black hole would actually look like when they saw it. And they caught exactly that. It was really quite an amazing feat.
I've seen it described as what they actually captured was the shadow of the black hole.
Mm-hmm. Yeah. Well, I always had trouble with that, because what they're actually capturing is the warpage of space and how the light follows the warp of space. So what they're saying is that's the shadow. It's really not a shadow. It's not casting a shadow. And you're right. That's how they've described it, but it's not casting a shadow. Yeah. It's just that curvature of space.
Izabela, everything is not expanding equally outward. Part of the point of that balloon analogy, the farther apart any two objects are on the surface of that balloon, the faster they are accelerating away from each other. That's one reason I like the raisin bread analogy. It carries it straight to 3 dimensions instead of sort of being a 2-dimensional thing, spread out to 3 dimensions like the balloon is. If you have a loaf of raisin bread rising in its pan before you bake it, those raisins, 2 raisins next to each other, are moving relatively slowly, while 2 raisins at the far ends of the loaf of bread, they're moving much faster away from each other.
I understand that analogy. And the only reason I use the balloon one is because you can visually watch it and see what it's doing.
Yeah.
And then you can, when you see the black spots on the balloon as you blow it up, you see that every spot is moving away from every other spot. Now that's just a two-dimensional shell, a three-dimensional shell, but the universe is three-dimensional, so you still have to make that intuitive leap to fill the balloon with other stuff that's expanding out. But it's following the same behaviors as the other stuff, relatively speaking, if you draw a line in from the outside of the balloon. So it's like you took a snapshot of the balloon every microsecond as you blew it up and turned that into a model. You would actually see that the farthest dots or galaxies from you are moving the fastest away from you and go the farthest, of course. And so that led to that quality and property of distant galaxies that Hubble called the redshift. And we actually see redshift when we look at objects like galaxies. We'll actually see the redshift parameter given. And from the redshift, you can actually calculate that's the recessional speed. You can calculate a lot of properties of the galaxy, a few properties, from the redshift.
Mm-hmm.
Yep. Neat stuff. I mean, I love it.
And Michael says Andromeda is moving toward us. That's local space, relatively speaking. Where you get into the cosmic or cosmological redshift, you're talking, like on the scale of superclusters and things like that.
Right.
Much larger scale.
Yep. That is so true.
Andromeda is part of the local group, along with the Milky Way and a group of other galaxies, and that's so-called local space.
Yeah, and see, the thing you can think of is local galaxies can be moving around each other, okay, while they're all as a group moving somewhere else. And that's kind of what's going on here. And so we're gravitationally bound with 20 or 30 other galaxies, 20 or so other galaxies.
Yeah, and then the entire local group is moving
toward Virgo,
or falling toward Virgo, supercluster or Virgo cluster, and then the entire Virgo cluster is pulling us along with it as it moves toward the Great Attractor, which is down in
something
the southern
else.
sky.
Yeah, and if you actually want to really pop your brain into a little pile of mush, look up Laniakea. All right, Laniekea, Laniakea, Kea. Sorry, and you can look up the concept of what's going on with the superclusters of galaxies, and you'll see that it looks like a neural network, which is very interesting.
Yeah.
And the people that like the Gaia hypothesis love Laniakea. All right. Well, we're done with this one. This is gorgeous, but we're going to halt this at the 76 we've done so far.
Don't forget to name it.
I thought I did. I was about to when I got sidetracked. If I didn't name it, it'd show up as a number.
All right. Izabela, no, the Great Attractor is not part of the local group. As Marc said, the local group, you're talking maybe, I forget, 20, 30 galaxies, something like that. Yeah. And we are falling toward the Virgo cluster, which is the big local cluster. The Virgo and everything else, Virgo cluster and everything else is moving toward the Great Attractor, which is much farther away, and it's way down in the southern sky. I want to say it's in Triangulum, Australia, the Southern Triangle.
I don't know.
I don't recall for sure offhand. I think that's where it is.
Well, the thing that's interesting, though, Darrell, as you point out, we are heading for the Great Attractor, but keep in mind, and for all you guys listening, remember, we have all these galaxies that we're gravitationally bound with. And long term, we're doing this. We're all moving around each other, colliding, and so forth. But as a whole group, we're moving toward this our other thing. So it's extremely complex movement. Long term. And like when we do proper motions, for instance, proper motions are the motions of stars, right? We can get them for galaxies and get their galactic motions. Well, that's just a snapshot. It doesn't take into account what could happen in the future as a galaxy is being curved around by another gravitational object and whipped by it. We don't know that. We can tell by mass whether something is gravitationally bound to something else. We can understand that and calculate by how much it's bound. What we can't calculate is what will happen to it. Okay, and that's the mystery that we don't understand.
Yeah, and that's on such large scales of distance and time that
Yeah.
You know, it's not even astronomy or astrophysics; it's cosmology.
That's right. And I always say this, cosmologists tell you how it all happened. Astronomers tell you what it is, and astrophysics folks say, and this is how that particular process works. They're very similar but very different branches of the global science of astronomy.
Well, where are we going next?
I am going to take us to, I'm going to come up here, I want to go and check out some of, I think it's dark enough to see these, we can check it out now. There's some galaxies in Leo that we haven't seen yet that I'd like to check out. I think I still have them showing. Yeah, I do. Let's zoom in more. There we go. We saw M95 and M96. We saw M105. But I was thinking, why don't we just go to this nice galaxy-rich location right here and check them out. We have M105 down here, NGC 3412, and this one here is what? Oh, 3367. Okay, yeah. So we try that?
Sure.
All right. All right. So let's do it. Okay. And off we go. And now we got our 1 second exposure. Telescope is zipping away. Look at it over my head, moving like crazy. And it looks like we're going to use Regulus as our star, or maybe not.
I don't see your keypad tonight.
Oh, it'll be there as soon as I. Yeah, it's there. You'll see.
All right.
Yeah. Okay, so we're centering a star right now. So let's bring this star in. Not sure which one it is. It would show if I had to remember to. Like, there's a galaxy right there we just missed. Okay, so now we should be over in galactic realm. And we are, look at that. And I'm at 47% here on our sensor. Let's go back to check out the entire view of the screen. This dark center is because it's not quite dark out there. And this is a correction that I'm making right now to the images. If I wanted to, I could just dispense with that for now. I don't know that I want to, but I'll just show you what the difference is. Okay. So right now, if I were to just shut this off, all right, then it would look just like that. And you say, wow, that looks so much better. Well, it does until you start taking pictures. Once you start taking imagery, then you get a brighter center. And that's not good. We don't want that. So it's called a flat frame. And we want the flat frame. So I'm going to put it back. Because otherwise it's a correction that has to be made. Okay. So let's do this. Let's come back down.
Vera's here.
Vera is here.
Hi, Vera. Yes,
Vera
ma'am.
Lucia Campos. Hello. Welcome to you, coming all the way to us from Brasilia. You are more than welcome. And let's do this now. Let us. There's a galaxy there, galaxy there, galaxy there. I'm going to bring us down just a little bit. Get rid of the top galaxy, but I'm going to bring these in because these are sort of the stars of the show right now. A little more.
The bright one at bottom is that M105?
That might be M105 right here. Let's go look at where we are placed. This is where we are. Hang on.
M105 is part of 3.
Yeah. Where are we over? Might be over just a bit far. So that's okay. Yeah, there's 3 right here. See, 1, 2, 3. That's
okay.
That's
Yeah.
M105.
Yeah.
Okay. All right, let's try this. We're gonna set our exposure up to let's say 25 seconds. To see all these distant galaxies in 25 seconds is kind of cool. And let's bring up our sensitivity to 300. All right, 25 seconds and go. And now I'll bring up the live stack and clear the last stack of the Seagull Nebula because that'll be in there. God, that's a beautiful nebula. Wait till you see the summer sky, guys. Oh, it's gonna be just so incredible. All right, here we go. First one coming in from this section of Leo. Wow, look at that. We have a lot of galaxies in here. Let's color correct that right off the bat. Okay, let's take care of that. All right, and then let's do some processing. Get our curves arranged. There we go. Now look at all these galaxies we have. This is M105 right here. All right, and M105, let me bring it back to Stellarium for a minute. M105 is this guy right here. And M105 is an elliptical galaxy, but one that's almost round. It's just off around the tiny bit. So instead of an E elliptical 0, it's an E elliptical 1. Okay, E1. And you can have an E7 or so. I mean, there's various forms. The more elongated, I think, goes to 9. So this is beautiful. Yeah. So in this one shot, we have 1, 2, 3 galaxies. We have a 4th galaxy here, a 5th one here, and one out of shot that we just let go up there. And we have one right there, a little tiny one. See that? Now here's something to think about. Looking at these galaxies, you have to wonder, are we looking at life elsewhere? I tend to think we are. I think that life is more of the rule, not the exception in the universe. But that's just me. There's people that think I'm all washed up. But I don't know. Do you think I'm washed up? I think that people just don't actually, the ones that don't believe it, I think are just too heavily invested in modern dogma to actually question it. And I question it. That's how I've gotten to where I've gotten by questioning everything.
I've always been of the thought that, it's such a big, beautiful universe. It'd be a shame if there wasn't anybody out there to enjoy it.
That's right. Yeah. If we find life elsewhere, that's amazing. But if there's no life elsewhere, that's a miracle. You know? Let's try zooming in now down on M105. Thank you, Izabela. There we go.
Satellite.
Yeah. Yeah. I see double trails a lot of times. Interesting. I've always found it just below 105. This galaxy is actually the most intriguing one to me. It looks really interesting. It has a very fascinating spiral structure that the others don't have. You see that? It has a nucleus that's off-center. And I'm not sure why. I don't know how far it is relative to these. We could find out right now. But it's kind of interesting. Let's go look. Alright. So let's go here. And go here. And this is NGC 3389. And how far is that guy? Okay, his distance is 80 million light years. And how far is M105? 31 million. And then NGC 3384 next to this, 26. So this one is much, much further away.
Yeah.
So, I mean, it looks it. This one is much further away than these guys, which are in the foreground to us. But they're all in the far distant background to any of the stars you see in here. It's a 3D universe, folks. Izabela says, by the cosmological principle, that everything is the same everywhere in the universe. Life must be everywhere in the universe. I also would say that that's probably true. Not for that reason, though, but I think that it really comes down to the fact that we're carbon-based, and carbon is the fourth most abundant element in the universe, next to oxygen, then helium, and then hydrogen as the most abundant. And so carbon is going to play a huge, massive role in this universe, without a doubt.
So the one at lower left is 80 million light years away.
Yeah.
The one at upper left was, what was it, 24 million?
Just about, yeah. And this one was 31, I think.
Yeah.
Yep. Really fascinating.
So it's safe to say that M105 and the one to the upper left, I mean, they're farther away from each other than we are from Andromeda.
That's right. But it doesn't mean that they haven't interacted.
Right.
You know why? we don't know what makes these elliptical galaxies. You know, like this elliptical right here, right? It has, the thing about ellipticals is they don't really have much gas in them at all. They have, and you know, there's no dark clouds of dust. They seem to be relatively dust-free compared to other spiral galaxies, and yet they are an elliptical collection of stars. So where do those come from? You know, how are those formed? That's the question, and we actually have ideas, but we don't actually have any definitive answers for how these guys are formed, because there's less gas in these than in these other galaxies that you see, and there's less material in here, and the stars are all, you know, pretty much done forming. So what causes those? What causes these to actually form like that? That's the mystery, and that's something that we're still trying to figure out. Fascinating. Fascinating, Captain. Mr. Spock, I understand. Okay, let's get out of this. This is, we're going to call this the M105 region. So we'll pause the stack. Hello there, weird guy. How you doing? Weird guy says, bought a telescope at Goodwill today. $14. It's missing a few things. The mount. But I think I can rig it up. It's 114 millimeter celestron from China. Wow, that's pretty nice. That's a nice little scope. I think that's at the. It's a little bigger than the C90 spotting scope that they had.
Marc,
So
I hear you twice, Marc.
okay. I don't know why. Is that just suddenly? Is that just suddenly, Darrell?
It was when you were talking about what W13 was saying.
Okay. And how about now?
I still hear it. I also hear me.
Okay, that has to be.
Oh, okay. Sorry, I had my mute went off on YouTube stream.
Okay, that's what it was.
I was hearing the delay.
All right.
Sorry.
No, that's actually good. You know why? Because you got us a couple more exposures on this this shot right here. Okay, we'll let this one finish out to get 25. Go ahead.
Vera, I have a question. Vera, the Andromeda Galaxy M31 is, I've seen various numbers, 2 million, 2.5 million light years from us. The Magellanic Clouds are less than 1 million. You're talking maybe 250,000 light years away. A couple 100,000. They're much closer. They're, like 10 times closer than Andromeda is.
Yeah, and they've already interacted with us, and they're still interacting with us.
Yeah. They are, the Magellanic Clouds are satellite galaxies of the Milky Way.
Yep. Okay, we are done with this guy.
And Genghis is here.
Hey, Genghis, how you doing? Power Seeker 114 EQ. Okay, that's a reasonably cool little scope. You should try it on some terrestrial objects, especially. Don't you do the weird guy? I think that's what your W13 RD is supposed to be. Take the telescope, and when you look at an object, try looking at a long branch, and see if you see any colors in it at the edges. Okay, like a blue edge, or a red edge, or a red line. That's called chromatic aberration. That'll tell you the quality of the optics in that scope. Okay, Judy, thank you for coming. It's really nice to see you. I appreciate that you came. And we start later as the summer months approach because it doesn't get dark out there until now. But we'll see you later. Thanks for coming. So try that, weird guy, and put that on an object that you can you see as a linear object, like an edge of something, top of a building edge or something, and just see what you see if there's any separation in colors. I'd be interested to see how that works. All right. Back to this. Here we go. All right. All right, we did our M105 thing. Now what I'd like to do is take us up a bit. There's so many galaxies to see. It's absolutely...
in the neighborhood, we ought to go down and look at 95 and 96.
Yeah, we can do that. Sure.
I mean, we've been there before, but...
All right.
They are more photogenic.
They are. So here we go. All right, we're going to go here. We're going to go right to this spot. So let's do it. There we go. Oh, I forgot to bring back my display here. Sorry. That's okay.
Well, did you name the last one?
I did.
Okay.
Yeah, I call it the M105 region.
All right.
Alright. And now we're going... Let's see what star it's using as a waypoint star. Oh, okay, it's over there. Alright, good. Alright, here we go. Here's M95 and M96 right here. I believe this is M96 and that's M95. Am I correct on that? I think I am.
Yeah.
So this is beautiful. So these two beautiful dear sweet galaxies look beautiful under time exposure, and we're going to get those up and running for you. I want to actually try and do something a little different. We're going to move him up out of the way just a little bit so we can center this up a little. And now we're going to zoom in 250% just to see our focus. So it'll become somewhat pixelated, and that's fine. Focus looks pretty good. And now we'll back out. Okay. And we're still searching for a star. We got this guide star. See that? When you see numbers showing up and you watch the numbers start changing, it means that we're guiding. And now we're guiding. So, we can now say, let's do 35 seconds here. And get rid of our hybrid view over there. So I take that off and I reduce the amount of the data we're picking off of the sensor here. This is all the data coming in right there. And I just reduce it to a little tiny bit so it gets a little darker. And then we go to our live stack. Right now it's building up on the sensor, and then once it's ready, it gets read out and displayed. So all we have to do is wait. Let's see what we got coming in. Here we go. Look at that. That's beautiful.
Yeah. And that's
it never
that
disappoints.
M105 group still up at the top left.
That's it, because now we're just south of all that.
Yeah.
So if we look at our stellarium view, okay, we're actually seeing M105 up there, and then that galaxy that's right there and there. This is those three galaxies we looked at. This one's the 80 million mile distant, 80 million light year distant one. This 21 or so, and this is like 31 or something. It's something along that line. I forget what we said, but it's really cool. All right, so let's pull this up a little and zoom in a little bit.
I remember when the Meade ETX came out.
Yeah.
Bonnie and company there talking about it.
Yeah.
When the ETX first came out, the neighbor got one across the street, and I don't know if you ever heard of a telescope called a Questar.
Oh yes.
Which is a very fancy, very expensive portable telescope, thousands of dollars. And the ETX was like a copy of the Questar, made by Meade. And it was only hundreds of dollars, not thousands. So the quality wasn't the same, but you get what you pay for.
Yeah, the Questar was a
Maksutov. I'm sorry?
It was a Maksutov, wasn't it?
I believe you're right, yeah.
Different telescope design.
Yeah. Questar's kind of telescope you buy if you win the lottery.
Yeah, back then it was $3,500 back then, when telescopes being $600 were a lot of money.
Yeah.
And then you had this telescope that was $3,200. Like, why in the world? And it was only a 3-inch diameter telescope. Why in the world would you want that? That's what I always said.
And
I want a light bucket.
Questar used to sell a large one too. I forget. I've never seen one. It was like a 7-inch version. It was a fairly good-sized telescope.
I remember that.
Yeah, and they were really expensive.
Yeah.
All metal construction, very fancy exteriors on them. They had
the tube had the constellations on it.
Yes.
Wow.
I like 95 and 96 so you can see the spiral structure.
I know.
Easily.
I was never a fan of the elliptical galaxies,
Yeah. Well, they just look like big fuzzballs.
Yeah.
When we see M87 in Virgo, it's the biggest galaxy in the Virgo cluster. It's elliptical. It just looks like a fuzzball.
It does. Looks like a spherical fuzzball.
Yeah.
It could pass for a star.
Dr. Fox 2000.
Oh, is he here?
Yeah.
Oh, there he is. Hey there, Dr. Fox 2000. How's it going? He writes, "Good evening, Mark and everyone. Just lurking and waiting for you to hijack the James Webb and point it at exoplanets." Haha. Hey, man, you got it. I'm not going to have to hijack it, though, Dr. Fox, because they've already got looking at exoplanets on the docket, so we're good. We're good.
Did you see that article I sent you this afternoon?
Yes, I did.
Yeah, more new images from the web.
Yep.
It's still in testing, but they're saying it's well focused now and pretty much ready to go. They've got to commission all the instruments now.
Yeah.
But they've shot a lot more test images with it, and they're pretty spectacular.
Yeah. I want to say, before I forget, Dr. Fox 2000 here is, he runs one of the best volcano channels on YouTube. So look him up, Dr. Fox 2000, and you'll see some of the best commentary and discussions about volcanoes on the planet, frankly. And one of these days, Dr. Fox, you're welcome to join us on the air if you want to join us at some point, and discuss some of the eruptive activity in the world, we'll be happy to do that. So that's your call. Whenever you want to do that, we'll be happy to host you here and have you come on with us. Yeah, so go check out Dr. Fox 2000's YouTube channel. Make sure you subscribe, because some channels, they have people on there that just talk about volcanoes, and they kind of talk through their butts. Not many of them are as smart and actually considerate of the actual science as Dr. Fox is. So I would recommend that you check him out. What are you doing still here? Go check him out. Just kidding. But thanks, Dr. Fox.
Remember, you all talked about Krakatoa.
Oh, yeah.
And not Krakatoa. The last visit he was here.
Yep.
And maybe it's one of those weird YouTube algorithm things, but I think it was like the next day YouTube threw a Krakatoa video at me.
Yeah, well, I think there is some kind of something to be said for that. That's neat. These spirals that you're seeing here. These are barred spirals. You can see that. What's a barred spiral? It's a spiral that it has arms, but it has this bar through the middle. And there's a nucleus, but then there's an extension to it, like a physical bar. And that's just what you see. Oh, thank you, Izabela, for putting up his channel. That was really kind of you. Worth every visit, guys. Check him out. Subscribe. Be part of his whole family over there. It's fantastic. I am. Here's another bar right there. You can see it moving across there. Looks like a steering wheel here, Darrell.
Yep. I was about to say, it reminds me of M109 we saw last night.
That's right. Well, this is, again, the differential rotation in the barred spirals and the spirals will cause them to kind of connect over time, their spiral arms, and they will look like one thing. I think that if you notice, there's gaps in the ring here, and these gaps, I think in a spiral you get those gaps as well, and sometimes through interaction and density waves, the ripples I talked about going through these spirals instituted by other spirals interacting with them, I think those lead to that really, really strangest of all configurations, the ring galaxy. Mm-hmm. And you can see how the ring galaxy happens when you look at the computer simulations of these over time. You actually can see the ring galaxy form, and then it goes away. So when we see a ring galaxy, it's a transitional phase to some other type. All right, so that's not a final phase. That's why they're so rare. It's a transition to something else. And we just happen to catch some of these over time that have transitioned, or in that transition phase. All right, we're at 15 stacked here. We're going to say good for that. And we'll let it go to 16 here in just a minute, because that's coming right up. And 16 stacked. Now we'll pause. And we'll save it. And you'll see that we're saving our FITS file up there. There it is. The FITS file. That's saved to our online database. You can go up there and check it out. And then save exactly as seen. And you'll see a different line there, saved as a ping file. You can now double click on that up on our server and see it just like you see it here. All right. And
Marc,
that's what
excuse me a moment, please.
Sure.
Be right back.
And that's what we do, and we do that for you for nothing. I must be crazy, but let's hope that I don't change my mind ever. All right. So, let's go and go to our 1 second, go to our enhanced view here, and go down to auto. We're gonna fill the frame with our entire sensor so we have it filled out. There we go. Okay, now I'm going to come down here and let's go see. All right, let's go look for something. I know what I want, so that's where I'm going. Let's get close in here more. We looked at that yesterday. I think what I'm looking for is it M109? Or did I just make that up? No, see, that's what okay, that's where I wanted to go. But I wanted to actually see a different one. And we're going to look for that one first. I still have the delays. Oh, come on. I'm typing it in, but it's taking time. There it is. There we go. Okay.
Where are we going now?
Pinwheel Galaxy.
Ah.
Because I think we would like to see the Pinwheel Galaxy again. It really is a beautiful, stunning galaxy. And tonight, I think we're going to take a little longer exposure of it. So we don't have wind, and I want to take advantage of that. Just got to watch to see the telescope is now heading into the northeast. And let's pull out of here and see what star it's using. I would have known if I remembered to tweak our hand wheel handset. No problem. Oh, okay, good. Alcade. Right, it's using Alcade, and we're going to put the pinwheel right in the middle of the view. Alright, after it does that, there we go, and now we'll see the pinwheel showing up, I hope. There it is. Right there. Beautiful. Alright. Now we're going to increase. Hey, James Dugan, how's it going? Alright, and let's go to 250%. Just check the focus, make sure we're good. Okay, focus looks okay. Alright. Okay, and now we're going to do a 50-second shot. And first, before we do that, I'm going to actually get our star lock here back running. It's been running, but I'm going to get the I'm going to get this to do what it's supposed to do here. Alright, as soon as it finds something, it's going to start guiding. There it goes. And now I can tell it to do its thing. So off we go. The Pinwheel Galaxy is just beautiful. And so in this galaxy, it's face on to us, so we can actually see the spiral arms and just how they are come out of the nucleus, the core of this galaxy, and just line back beautifully. I mentioned yesterday, galaxies almost turn like a rigid disk, but not quite. So the stars in the middle do outdistance the outer ones a little bit, and that leads over time to a differential rotation where the outer areas, outer stars are lagging behind a little bit, and that leads to a spiral formation, and that tends to create a spiral arm. All right, but there is another thing at play, and that is something called the density wave, and that's another thing. Look at that. That's another object to, or another phenomena to discuss. And that's basically, a density wave is a strange construct because it's not like it's something that comes and goes. It's in the galaxy, and it stays in the galaxy.
Well, you could describe it as a standing wave, couldn't you?
Yeah, and it just like a traffic jam is like that. If you have I've used this analogy before. You have a red car, and it drives on the highway, and it comes into a traffic jam. There's a cluster of cars. It slows down, it makes its way through the traffic jam, and then comes out the other side. But the traffic jam is still there. It's just got all new cars in it over time. So that is a density wave. In fact, by definition, a traffic jam like that is a density wave. And it's like a ripple that is in a galaxy, probably and most likely induced by a nearby galaxy that has been interacting with it. And again, the universe has nothing but time on its hands, so these ripples and these density waves could have been introduced long ago. Now, you can look at elliptical galaxies, or like the Virgo galaxy, okay, M87, and you say, well, look, that's just a big round soft-looking body, a blob. So maybe it never actually had spiral arms. Well, that's possible entirely. Or maybe it had spiral arms that went away over time. That's also possible. We don't know. And that's how it is. We don't have all the facts on these things. But I do know that when we look at spiral arms like this, it's really hard not to look at these and say, oh, wow, this is just so stunning. I mean, look at that.
Yeah.
Only here do you see that.
That's obviously gravitationally interacted with something.
Yeah, because here is a spiral arm that's got this little bend in it.
Little? That's a great big bend.
Well, that's I guess okay.
And the next star I'm in has a bend in it too.
Yeah, it's not as obvious as the other arm, but you're right.
If you follow the curvature of that second arm over to the upper right, you can see how distorted it is farther back too.
You mean this here?
Yes. It's like a great big void in the middle of it.
Oh yeah.
And then there's an inner part of it also.
Yep.
And when you were zoomed out, you could see several other maybe possible candidate galaxies that it did interact with.
Yeah, there's one down below here.
Yeah, there's one there to the upper left, and who knows how close or far those other ones really are, though.
Well, I mean, if
beautiful galaxy,
it is. Dwarf. Well, any galaxy that's face on like this is always beautiful.
Oh yeah.
It reminds me of the whirlpool in some ways. Without the interaction, its particular interaction. It's a
big, beautiful galaxy.
Yeah. Let's see what it wants to do for the processing.
I thought that you were talking about ellipticals. There you go. I thought ellipticals were thought to be like conglomerations of other galaxies. They all got absorbed into the big elliptical.
Yeah, but it's a hypothesis. That it's not an actual factual. It doesn't have any merit in terms of, well, not merit. It doesn't have any proof. So it is only a theory. It's only a theory.
Yeah.
Look at that, huh? This is beautiful, guys. The pinwheel. Let's zoom in. We've got 6 stacked. We can probably go a little more. Yeah. Yeah, we got more to go in order to make this look better. What we could do right now to help it along is we could go into our stack, go into enhancement, and turn on the unsharp masking.
W13, I think the crab is down. If not, it's so far down in the west that it's probably murked out so bad it's not worth looking at.
Yeah, we wouldn't be able to really see it. I think it'll be below the observatory threshold right now.
Yeah.
It won't be after I put the lifting columns in, though. Okay. That's pretty. Okay, let me... I'm going to do something odd. I'm actually going to put on the bilateral filter now. And watch it get soften up the noise. There you go. That's nice. So this is what you get with us, you know. I mean, we're actually making we're showing you these things like live in seconds, you know. This is a live stack that's going on right now as we speak, you know. And I think this is pretty cool.
Yeah, Taurus is down completely.
Yeah. Okay. And this is our object.
Oh, that's a showcase galaxy if there ever was one.
Mm-hmm. And it sparks all kinds of conversation as to, like, why do we see this? Why is this crook here in the arm?
Yeah.
What did it interact with that caused that, you know? So.
Oh, and that crook in the arm, I think we talked about this last time we had.
Yeah, dude.
101 up. That this is Messier 101, folks. I think I might have had a Hubble image of this open, and there is so much going on in that left-hand crooked
here.
arm. Yeah.
This might be
that
might be an
particular
OB association. Might be like hot blue stars in here.
Yes.
And the spiral arms in general are bluer than the core. Here's a ring of hot blue stars that have formed. This is a ring that's like 30,000 or 40,000 light years in length in an arc or more, and it looks just beautiful.
Dr. Fox asks, how far away is the Pinwheel Galaxy?
Well, let's go see what this says. I don't remember offhand, so we'll see what it says. We are looking at a distance of 20 million light years here. Actually, that's actually relatively close for a galaxy, to be honest.
Yeah.
But 20 million light years affords us the ability to see a number of objects in here. Notice as we stack more, the galaxy data looks better and smoother, but the noise out here looks kind of rough. That's the benefit of stacking. Okay, we're gonna get rid of all that over time. Yeah, and if I turn off the bilateral filter, let's see what that does for us. See, the bilateral filter now levels the playing field and actually allows us to see our data. And one thing I'm going to do right now is I'm going to just advance that dark level just a bit. So we're going to go back into our histogram tab, I'm going to grab this histogram var here, which is the dark level. I'm going to advance it just a tiny bit to the right. Okay. And so that gives us just a little more contrast, I'd say. So here is more hot, bright stars here. These are very young, hot stars forming in these spiral arms. Again, that's where the dust and the gas tend to accumulate when the shock waves or the density wave was rippled into the galaxy. It caused this material to move into a natural spiral, and of course, as the galaxy rotates differentially, then you actually get the condition where that material is drawn out against itself, and gravitational condensation or contraction rather is enacted upon the neighboring particles, and you end up getting particles brought together. So you end up getting, overall, you get a star formation burst in these spiral arms, and that's what happens. We see lots and lots of stars forming in the spiral arms of most spiral galaxies, and that's why they're blue, because the youngest stars are usually really hot and blue. Betelgeuse used to be a hot blue star. It used to be an O-type star, and it evolved away from being hot and blue when it started to bloat and get large, and it got bloated and large when it used up all of its hydrogen fuel. So when it was first created, when it came into existence, it first winked in, it was fusing hydrogen into helium in its core, and then it went on to use all that up, and so then it began to collapse, and when it collapsed, more hydrogen came into the core as it was drawn down in, and renewed that burning again and renewed that fusion process. And then as it did that, the temperature increased and increased until it reached a certain temperature that helium could then fuse into carbon, and that started a whole nother bloating phase. And so the star just went through these bloats one after another until it finally reached a diameter that went from an O star that might have been maybe out to the orbit of Venus or Earth in size, to at the most, to being out past the orbit of Mars almost all the way to Jupiter in size. That is a really big three-dimensional sphere in the universe.
I posted a link to the wiki on the Pinwheel.
Okay.
It says it has about 1 trillion stars in it. It's comparable to the Andromeda Galaxy.
Mm-hmm.
Wow. 6 prominent companion galaxies. Gravitational interaction between it and its satellites may have spawned its grand design pattern.
Mm-hmm. Yeah, and that grand design pattern includes the spiral arms and perhaps some of these bends in the spiral arms.
Yeah.
That's not bad. I mean, this is a 50-second set of exposures, and we've done 16 of them. So that's pretty good. We're getting a lot of data here, guys. Let's try seeing what it wants to do. I'm going to guess it's pretty close to what we already have. And it is. I'm going to move the dark level in just a bit. Oops, I might have moved it too much. Yep. However, it shows you there's an awful lot of data in here. Look at how complex that inner area is. That's beautiful. You can see the complex dark nebulous lanes in this galaxy. It's really pretty. All right, let's bring back some of the galaxy. Here we go. Let's try and drop some of the noise a little bit. Okay.
Hey, here's one we haven't tried yet.
What's that?
Sunflower Galaxy. I don't think we looked at M63.
Yeah, we have not. That's all the way on the other side of the sky again.
No, it's near M51. Sunflower Galaxy is part of the M51 group.
Oh. And I'm thinking of another one.
Yeah. I was reading about the M101 group here.
Okay.
M101 there, and its companion galaxies.
Okay.
The M51 group is located, blah, blah, southeast of M101 group.
All right.
And the NGC 5866 group is located in the northwest. The distances to these three groups are similar, which suggests that the M51 group, the M101 group, and the NGC 5866 group are actually part of a single large, loose, elongated group. And they say they're all part of the Virgo supercluster.
The takeaway from this, folks, that you take away with this is that galaxies are very rarely alone. They're usually in groups. The groups interact with each other, and as a group, they move through the universe, attracted to other things with their gravity. And remember, gravity can act over a very, very long distance, an infinite distance. Okay, it doesn't whittle away to nothing over time and over distance. It actually is a powerful force, yet it's a weak force. I hate to say it that way, but it's actually a somewhat weak force. All right, so I save this, and I'm going to clear these now. I think I saved it. I know I saved it, but I'm going to do it again, because when in doubt, do it twice. It's better to have two of them than not all of them. All right, so there we go. And now we'll clear this, and we're going to go to this. This is going to be a beautiful image when we work on this. Look at that. It's beautiful now. It really is.
Yeah.
All right.
Let's try M63.
Yeah, that's a good idea.
Sunflower Galaxy.
Yep. So let's go back to our 1 second shot. Go to our hypered view. And go to first thing is first. Let me just tweak our system here to get our stuff back, get our visuals back. All right, now we're going to go to the Sunflower Galaxy. I've seen this. We've done the sunflower from here, but I'm going to do it from there now. I like that idea. Okay. Oh wait, it measures 63, so let me just type in that. Yep. Alright. Should be right nearby. And away we go. Alright, we're doing our precision slewing here, and we'll see which star is going to be brought in. You can see where the telescope's pointing right there. It's right there. And Cora Caroli. Alright, Cora Caroli will be centered, and we are actually at 66% here, so let me go back to our auto fill of the entire camera frame into the view. And there's the sunflower. Alright, we're searching for a guide star here, and once we do it, we'll be able to do our picture. We'll do this one for 40 seconds. Once we start guiding, I will commence the photo. Here we are. We're guiding. Off we go. Oh yeah. Yeah, Darrell says we barely scratched the surface, and you're right. We have barely scratched the surface. There's so much to see.
I want to say, you ever read the Timothy Ferris book, Galaxies?
Oh, I never had it. I actually looked at it, but I never read it. No.
It's a great book. It's probably outdated
Beautiful.
nowadays. It had great
Oh, beautiful
images.
imagery. Yeah.
Yes, and I think M63 was the galaxy on the cover.
Really?
Yeah.
Okay. Well, let's go in here and start getting ourselves acclimated to this galaxy. All right. We need to get rid of some noise, or actually let the stacking process rid us of some noise. You see this mottled colored noise in here. Okay. In just 5 seconds, the next exposure comes in, and you're going to watch it diminish by half. Ready? Watch this. Boom, look at that. So that's because we stacked images on top of each other. And the more we stack, the less that stuff comes into play. Very nice. Very nice. Evening wear. Nice. Remember that commercial?
Vaguely.
I think it was for Wendy's.
Yeah.
All of the runway models were coming out with burlap bags on. Swimwear. Very nice. Burlap bag. Evening wear. Nice. Very funny. Look at the beautiful spiral structure in here. You cannot miss it. Let's start zooming in. We've only stacked 3, but it should be enough to show us this beautiful structure. Look at that. Look at that. That's really stunning. A lot of modeling in there as well. And we can actually pull out some detail by just doing a little of this. We're going to pull this down just a little bit. And now you can actually see some really cool detail in this disk. That's pretty cool. So see, just taking the image is one thing. The data's all there. But coaxing out the detail is just from, you have an understanding of how images are built up and how they're developed onto a sensor. And then you can kind of get rid of some of the bad things. If I went all the way down, though, there's only a limit to what you can do, because you come down here and you're left with just the nucleus. Well, look at that.
Yeah.
You can see detail in the nucleus that you miss.
Yeah. Well, what you just did, the nucleus is almost overexposed.
Yeah.
And you stepped it down some now, which is letting you see a lot more of the faint detail, I think.
Yeah, look at that. You can see those spiral arms. You can almost see them spinning.
Yeah. And it's a big dark arm across the very bottom, the front of it.
Right
what
here.
I assume is the front, yes.
Yeah. Now, if we go all the way down, I think that we'll still only go down just a little more before that nucleus is completely star-like. Yeah, see, because we'll never get rid of the nucleus, but we will get rid of all the arms. Okay, but see, in order to see all the detail, we basically want to. It's a happy medium. We have to try and say we're not going to go all the way, up here, and then blow out the galaxy. But then you say, oh, but we'll miss all the faint stuff out here. Well, yes, but if we actually were to, you could see more stuff. But it comes down to what makes the galaxy present the best. And what makes it present the best is something around, right about, I'd say right about here. this presents pretty well. You know, that's really nice.
400 billion stars.
Uh-huh.
Another one found by Pierre Machine, who sent it on to Charles Messier in 1779.
Mm-hmm.
Loosely wound arms. Flocculent galaxy. However, when observed in the near infrared, a symmetric two-arm structure is seen.
Yep. JSCO 77 asks, what makes this galaxy's center so bright? Well, all galaxies have a bright central bulge, you know, a nucleus that's pretty bright, because the stars are actually compact in there. So you're seeing the combined light of a lot of stars in a very small region. So it tends to be brighter. The spiral arms out here, of course, they're in a disk, right? The central bulge has some thickness and size to it, but the disk is a flat area that goes out around it and is only a few thousand light years thick relative to the bulge. So we don't ever see a disk that's brighter than a bulge in the central nucleus of a galaxy. So that's what makes it bright, is the fact that there's so many stars so compact in that one little spot. And also, of course, the way we're taking the picture. If I took a 1 second shot, well, then it'd be a tiny little spot. But again, that tiny little spot would correspond to a little tiny space that actually has a lot of stars in it. So it's cool. This is really exciting. This galaxy looks beautiful.
That's why I looked this up. It's
yeah, good idea. Really good idea.
The center is so bright.
Yeah.
It's a weakly active galaxy. Unresolved source. It's a nucleus, galactic nucleus, that is cloaked in a diffuse emission. Diffuse emission. Blah blah. Soft X-rays and hydrogen emission can be seen coming along nearly the same direction. If there is a supermassive black hole in the center, which is uncertain, if it does exist, and it's estimated as 850 million times the mass of the Sun, which is much larger than the one in the middle of the Milky Way.
Yes. Okay, we're up to 11 stacked here. Let's try pushing this a little bit to see if we can bring out detail in this arm here. I'm sure we can, but here we go. Push that in.
It is really bright.
Yeah. Yeah, you can see a lot of detail out here. It's almost like this is not the end of the galaxy. This is the end of the galaxy, you know?
Yeah, it goes even farther out.
Yeah.
There are that big dark bar we see across the bottom. There is more farther out that we don't see.
Well, you see it here. It looks like it's going like this. You know?
Well, yeah, there's a lot more out there. It's a very large galaxy.
Mm-hmm. Quite something. Let's go to our enhancements and see. Get the bilateral filter on. And let's go to 1.62 here. Yeah. Okay. And let's go back here. And let's play with our dark level a little bit. Let's move it just a bit to the right. Get a little more dark in there. There we go. That looks interesting. Wow. What's that right there? Is that little hook? Is that real or imagined?
Say that again?
See this little marker? See this little shape?
Yes.
Yeah. Is that real or imagined?
I'm sure it's real.
I'm not so sure, but it looks real. Very cool. So what do you guys think, huh? Hey, OG Skywatch, how's it going? Yes, we were talking about that before, OG. That the James Webb is finally ready for prime time, but they're going to be doing some more work with the instruments just to get them each finalized, and then we're ready for science.
Yeah, that article I sent you today said they may be another couple of months away.
Mm-hmm.
They're the next task for them is commissioning all the instruments. The telescope is collimated or aligned as well as it's going to be, they think, and now they have to test and commission all the separate instruments on the telescope.
Yeah. Okay, bilateral filters going off. Okay. Look at this modeling in here, guys. This is just so beautiful. Wow.
That's really something.
JSCO asks you, Darrell, you read If the Black Hole Exists. What is the controversy as to if it exists?
Give me just a moment. JSCO. M63. This is just wiki, okay? It's a weakly active galaxy with a so-called liner nucleus, short for low ionization nuclear emission line region. Blah blah. This displays as an unresolved source at the galactic nucleus that is cloaked in a diffuse emission. The latter is extended along a position angle of 110 degrees relative to the north celestial pole, and both soft X-rays and hydrogen alpha emission can be observed coming from along nearly the same direction. The existence of a supermassive black hole is uncertain. If it does exist, then the mass is estimated as 850 million times the mass of the sun. I'm sorry, that's what it says. Take that as you will.
Look at this. This is just beautiful. This is really gorgeous. I mean, the music's making it gorgeous too, of course. The majesty of the universe is unfolding before us. Wow. You can almost see the three-dimensionality of it in a sense. I wonder how many civilizations we're looking at.
A bunch, I bet.
And they're looking back going, I wonder if there's anybody out there. And some of their people at that end, or some of their beings at that end are going, no, there's nothing else out there. Little do they know. Wow. Alright, this is 21. We're going to go to 22 and then we'll stop here. Just a beautiful galaxy. Okay. Alright, now we'll save it. I've got it listed properly. And I will save it exactly as seen. Alright. Oh boy. Yes.
Your image is barely hinting at how, as the article said, it's a spiral galaxy, but they call it a flocculent galaxy. That the arms aren't strongly defined.
Yes.
And in images at the wiki, which I posted in chat, you can look at it if you wish. You see what they mean by flocculent. It's just the whole body of the galaxy is all like all clouds and chunks and stuff.
Like it's pretty wispy out here.
Yeah, it's all very. It looks like just huge collection of clouds.
Yeah. All right. Yeah. Well, we saved this, so we're gonna clear it now and go. Well, let's see. We've got this is 2 hours we've got so far. I do have to be up early tomorrow. I've got to go film for the TV show The Unexplained. I think it's on History Channel. So I am going to have to call it a night. But that was a beautiful bonus object we just did.
Yeah.
All right.
Okay, well, thanks for having me on, Mark, and thanks for coming, everybody. I hope you enjoyed it.
This is wonderful. I know it was a short stream, but you know something? It's better than not having one at all. Mm-hmm. So, you guys, I'll be back probably. Well, if it's gonna be clear tomorrow. Tomorrow's Friday. Maybe we'll do one Friday night tomorrow night. This is a time of year when it's pretty much clear all the time out there, so yay. I think, I know it was too short, James, but it was a good night with a few good topics, so we're cool. Anyway, you guys have a good night, and we will be back on the next clear night. So I'll just close up the stream, and then I'll take care of closing down the telescope. It'll take me another 15 minutes or so. In any case, Darrell, thanks for coming on.
Sure, thanks for having me.
All right. Okay, guys. Well, we'll be seeing you.
Good night.
There you go. We'll see you soon.
See you, James.